yeah? The angle restriction, or just, look at what cos squared does, right? Cos is between -1 and 1. Cos squared is between 1 and 0, okay? So the worst this can be is 0. It's not 0 because cos and sine are positive on the positive quadrant, okay? So no tricks there, okay? So then what? Well, okay, so theta, since theta is equal to cos inverse of x, this implies that tan, geez, tan of cos inverse of x is equal to the square root of 1 minus cos inverse of x, and then we square on the outside, divided by, this is just cos, so this is just cos inverse, bless you, of x, which is equal to, so what's cos inverse of x? X, very good. So this is nothing but 1 minus x squared divided by cos inverse, this is just x. And this is the answer we had last time as well, okay? So no need for triangles. If you like triangles, then whatever, right? But you can do the same stuff just using the formulas that we're given, okay, right? However, because we're in MAT135, this derivation is equally as important as the one with the triangles, okay? And I promise you, okay, there are questions like this, oh, a Ferris wheel is moving at this speed, blah, 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 blah. What is the rate of change of, et cetera, et cetera? You draw a triangle, basically, okay, right? Yeah. So you should know. Somehow the triangles are more, they're more in line with, they're more in fashion with this version of MAT135, right? Yeah. But if you don't like doing the triangles, this is an equally valid way of doing it. For x is positive. When x is negative, try doing it yourself, okay? Remember, the only thing that changes when x is negative is that the domain, right? The domain. There's a domain. X is negative, so theta changes. Some things change, but the derivation is identical, okay, to what we had last time. Okay, so with that in mind, let me give you one more question with the answer, and then we're going to move on to the lecture slides, okay? All right, so this is, okay, sorry for erasing it too fast. But yeah, let's see. So the next question that I have for you is tan CSC cosecant, right? Okay. So here's the claim. This thing is equal to. Okay. So first of all, domain. Are you kidding me? There's no chalk here, right?
This is a
What?
This is a
Yeah, fingers. Yeah, good idea. Right? Yeah. Nothing there? No? There's got to be something there. There's no way. Yeah, whatever. Okay. Okay. Maybe there's some in this one here. Whatever. Okay, nothing there? No? Please, no? Nothing? Does anyone carry chalk around? No? No one? Okay. The domain, okay, we'll try this way, right? The domain of this function is what? What's the domain of this? Well, first of all, domain is x in minus infinity, minus 1, union 1, infinity. So make sure you understand why that's the case, okay? Or you can derive why this is the case. That's the domain. Okay, so this is our f. And we want to rewrite it in terms of without trigonometric functions like that there, right? Square roots, polynomials, okay? That's the same goal. Please don't make me write it. This, this hurts. Okay, and then the claim is this. So if x, so x is in 1 to infinity, this implies that f inverse of x is equal to 1 over x squared minus 1. Okay, and if x is in minus infinity to minus 1, this implies that f inverse is equal to minus 1 over x squared minus 1. Okay? That's the claim, okay? So, how do you do it? Triangles, again. Triangles, or try using these algebraic formulas, okay? Right? So this one's a bit harder, okay? But not really. It's all the same at the end of the day, okay? And the goal here is to practice it so much that it becomes second nature. Okay, that's the goal that we're going for here, okay? All right, full screen. In the textbook?
是他把那个定式移到中间上面，他把那个定式移到中间来了呗。
I think it is. Okay. Okay, so I'm going to do something that you're not supposed to do, okay? What is it? Calculus, right?
Yeah.
Teacher, why don't put the computer for the class center?
Well, why
Why put that computer for the classroom center?
Sorry, what?
Like, do you want to put that in the middle?
Put
So
that
I
in
that,
will, yeah. No, I can pull down the things, right?
oh,
Oh.
Right?
oh, then why?
Okay, why is my thing in Hebrew? That's the crazy part. Okay, hold on. Okay, sorry. PDF. What's the name of the
Wait,
textbook?
what?
Okay, nobody's telling me? Okay, that's fine.
It's the Willy Plus, I believe.
Okay, nobody wants to tell me? Nobody even knows what I'm asking here, okay?
Like, what will it resources? It's on my textbook. Calculus. Calculus single library.
So here's what we're gonna do, okay? So you didn't see me do this, okay? And if you did, it's how do you go like this? Jeez, okay, anyways.
在干嘛？看都看不见。你看得清吗？
Okay, whatever. Anyways, it's in the textbook, okay? If it's on the textbook, we'll take a look later, okay? If not, if it's really not there, right, yeah, I'll make some questions of this, okay, right? And I'll post the PDF in our lecture slides, okay? So, but I will take a look, okay? How do I make this full screen? That's the question. Who knows? Zoom? Like this? No. No, that's crazy. I don't want this.
Wait, can you how about open up
Say that.
Yeah, open up in like the separate document.
Like this?
Yeah.
Like this?
Yeah.
Huh?
And
Is it? Okay.
there should be a square on the right.
Okay. Alright, there it is, okay? Okay, so once again, oh, what's happening? Okay, now how to make this full screen? I'm literally a boomer, okay? Like, I'm not even joking. How do I? Like, how?
Maybe.
Like this?
Oh.
No. You? This?
Yeah.
Very good. Please? Thank God. Okay, very good. All right. Okay, so once again, 135, etc., right? Yeah. Okay, right, okay, so learning objectives. Okay, did we do everything? Well, we did almost all of it in some sense. So by the way, just because we didn't cover it in class doesn't mean that you need to know what this arc length business is, okay? Make sense? Right? So for example, we didn't do arc length in class. It's in the book. It's here, so you have to know it if you want the appropriate grade, okay? Yeah, if you want like a A++ or whatever, right? Yeah, then you should make sure you know it. But if you want a B, then who cares, right? So anyways, yeah, so this is not exhaustive. Like what we do in class is not exhaustive, okay? Is what I'm trying to say. All right, anyways, trig functions, their transformations, amplitude and period. Do you remember what's amplitude, or do we know what's amplitude?
It's like the vertical stretch.
Okay, and what's the period?
It's the horizontal stretch. Well, I mean 2 pi in.
You were saying things.
The distance that it takes
Like
to do a
a
full cycle.
A full cycle of the Trig.
I'm getting like 10 different answers here.
Trig for
It's
me.
the, okay,
Tricky.
is period defined for all functions?
Yeah.
What?
No, that only applies to trig.
Only trig? No, only to periodic
The
functions.
repeat,
Not
yeah.
all. Okay, two things. Not all periodic functions are trig functions. Okay. However, almost all trig functions are periodic functions. Okay. Right. Just saying. Okay. So whenever you have a periodic function, can somebody give me an example of a periodic function that's not a trig function? Anyone? Someone? No. It's not. It's not. By the way, don't like just. One quick comment, right? Yeah. Whenever you don't have to think of the most complicated thing, right? Yeah? Just think of the stupidest possible thing, and it probably works. Okay. I'm not even joking. Okay. So the simplest one is called the sawtooth function, right? Yeah. And you can imagine what it is.
还有，但是我觉得可能
Okay.
不太
Right. Yeah.
他
So
他要的就是除了
something
这个，
simple like this, right? Yeah. Something simple like this that keeps going on, right?
应该还是可以除。
That's perfectly periodic, right? Yeah. Let's go backwards too, right? Yeah. Why not? Right? Let's say it's like 1 minus 1, whatever, right? So that's periodic, right? Yeah. So its period is the amount of time it takes to complete one full cycle, right? That's the point, right? Yeah. It's not 2 pi. It's, you know. Okay. So trig functions are like this, but not quite. Okay. Anyways, so and the amplitude is the the top minus the bottom, right? Yeah. Okay. Good. Very good. Assess whether a set of data or a graph is modeled well by trig functions and construct trigonometric models. We'll talk more about this today, okay? Okay, right, so today we're doing 1.6, okay? So there's something called local and global views, okay, right? Yeah, so local is local, global is like, they say mondial in Italy, right? Yeah, or we say, I guess. So local, global, okay, right? Yeah, and what's global, right? Okay, so is the interval, how should I say this? Is the interval minus a million to a million a global view or a local view, you think?
local view.
Right? Global? It's local.
Local.
Still it's local. Okay? First of all, I didn't tell you the units, okay? Second of all, right, I mean, I could have been like millimeters, right, or whatever, right? Yeah? So I didn't tell you the units, that's one. And global is truly behavior at infinity, okay? So no matter what number you think of a larger number, okay, right? That's kind of a concept of infinity that we're going to be talking about today, okay? And if you give me a finite number, you're still local somehow. Give or take. We'll talk about this in more detail, okay? Right, so we're going to talk about this local and global views and then end behavior, okay, whatever that means. And then we'll talk about rates, what is it? Ratios of, or rational functions, okay? All right, so let's dive in immediately, okay? Here's a polynomial, okay? Its expressions of the form p of x is an, x to the n, an minus 1, xn minus 1, a1 dot dot dot, a1x plus a naught, okay? Right? Where, okay, so n is an integer. That's something that I didn't write here, okay? N is an integer. Well, by integer, it's a natural number, so it's positive, okay? So for example, something like x squared is a polynomial. Something like x to the minus 1 is not a polynomial, okay? Make sense? N is a positive integer, so it's a natural number, okay? Right? And whenever we have this type thing, then the largest, look at the largest exponent, look at the non-zero guy, that's called the degree, okay? Right? Yeah? So a polynomial like x squared, that's a polynomial, right? The degree is 2, okay? And the leading coefficient is 1, okay? So I guess the question is, how many parameters are there here? N plus 1. Who says more? Who says n? Who says n plus 2? So why did you, okay, so the parameters are the constants, right? That define the family, okay, right? So there are n different constants that define, or n plus 1 different constants that define one polynomial, okay? So there's n plus 1 parameters, okay? With the linear function, y is equal to mx plus b, x is the variable, m and b are the parameters, okay? For a quadratic function, ax squared plus bx plus c, a, b, and c are the parameters, n plus 1, so 2 plus 1, that's 3, and x is the input variable, or the independent variable as we call it, okay? Right? Okay, So quick comment, if you know, so those of you who love the quadratic formula? As you know, versus completing the square. No? You know, quadratic formula is better, right? Yeah? Is it? Okay, so, right. If these words make sense, that is nice. So the process of completing the square is the process of finding the roots of the polynomials, okay? Right? Roots of the polynomials, look at the graph, look where it crosses the 0 axis, okay? Right? Y is equal to 0 line, okay? So completing the square is just one way to find roots of a quadratic polynomial. Quadratic formula is another way to do it, right? Yeah, it's a formula. These are just techniques, right? One is not better than the other. It's a taste thing, right? Okay, so you can do it for cubic polynomials as well, x to the 3 type polynomials. You can do it for quartic polynomials as well, which is x to the 4. X to the 5, those are called quintics, right? Those cannot be factorized, okay? So those do not have roots in terms of real or even imaginary, right? Those can be factorized. But even x to the x squared doesn't have real roots, right? Yeah? Do we agree with this? Do we know this imaginary roots business, right? Okay, so I can give you a polynomial that doesn't have, you know, doesn't cross the axis, right? Yeah? So, okay, so that's, okay, that happened, okay? Or we're aware of this, okay? So not every polynomial can be factorized. However, if you can factorize, a lot of the information is contained in the factorized form versus the non-factorized form, okay? All right, anyways, so how many roots can a polynomial of degree 2 have at most? At most 2, right? Yeah, it can have 0 roots if it doesn't cross the axis. You have 1 root, that's called a repeated root, right? X squared has a repeated root at the origin, right? Yeah, also, you know, it's like x times x, right? And yeah, so on and so forth, right? Yeah. So factorization is inherently related to the degree in some sense, and similarly, the degree is graphically the number of turns that your thing will do, right? That your polynomial will do. Okay. So an x squared, it will turn once, right? Minus x squared, it turns once. Okay. X cubed, it turns twice, at most twice or once. Okay, right? Yeah. X to the 4. It turns, you know, at most, anyways, it's hard to talk about it without drawing it, right? But try graphing different polynomials of different degrees, right? And you will see that indeed the degree is what determines how many times your graph turns, okay? All right, any questions about this? It's a bit abstract at this point, but that's okay. All right, graphically parameter fitting. We're not gonna do it today, okay? Because, you know, I don't have any writing equipment. But what I wanted to say here is this, right? If you have, so how do we do this, right? Given a set of points, right? Yeah. So what's the point of parametrizing or parameter fitting, right? Yeah. So ask yourself this: if you have a set of points that are given to you, they kind of look linear, right? Let's say, why not? It's clear that you should choose a linear model, right? Yeah? The polynomial you should be choosing is a linear function, right? Y is equal to mx plus b. And that way you only have to guess 2 parameters, m and b, right? However, you can kind of make x cubed work there as well, can you not, right? You can make x squared work as well if you stretch it well enough, right? And so the ideology here is, or the idea here is that given a set of data, you have to make a decision about what function to choose, okay? And somehow you want the simplest possible model, right? Yeah? You see what I'm saying? Or no? Does it kind of make sense what I'm saying? No? Said differently, okay? Said differently. Let's say that my data set looks like right? Let's say that my data set looks like this, okay? So, okay, I can kind of fit a quadratic here, can I not? I can do this. Can I not? I can, right? Yeah. However, remember sine and cos, right? Yeah. I can make a model like this, right? Yeah. I can also guess a sine function, minus sine, whatever, right? Check the amplitude, etc., etc. that also fits that well, right? Yeah. And so the question is, which one do you choose, right? Which one is the right one somehow, okay? And the answer is choose the one that's as simple as possible, okay? So so you're making two things, you're making two decisions. First of all, you're saying, okay, for this set of data points, I'm going to choose a, right? Or you could, for example, do an exponential family, right? Yeah, as well, right? Quadratics and exponentials maybe look similar on a small enough scale, right? So at the end of the day, it's a choice, right? Yeah, that you have to make. And most of the times in the exercises or in the exam, they'll be like, oh, fit a model that's exponential, right? Or fit a model that's of polynomial type, right? Or fit a periodic function, right? Yeah, it will be clear from the language, the type of function that you have to use, okay? So in that sense, we have to know all of them, okay? And yes, you don't need to know x to the 7, what those type of polynomials look like. But you have to know enough to, you have to understand enough. One of the Wiley exercises somebody was showing in office hours, it was giving you a polynomial that had 4 roots or something like that, or it had 3 roots, but it's clearly that you clearly have to fit in a quintic, or a quartic, whatever, right? Yeah. So somehow it should be obvious enough for you to figure out which function to fit, okay? Is what I'm trying to say here, okay? But at the end of the day, somehow all of them work, right? If you scale it well enough, all of them will work, okay? And so once we have a family, right, we just have to guess the parameters that will work, okay? So how do you do that? Well, you guess it, right? Yeah. You know that the function must cross this point and this point, right? Right? You know that the function must cross this point, and this point is this point, right? So 3, 4, 5, 6, right? Yeah. So somehow the idea is that if you have 6 points, if you're given 6 points, maybe you should use something like x to the 5, because you have 6 parameters, right? Yeah, n plus 1. However, it can kind of backfire, okay? Because of the following fact, right? So let's say that your data looks like this, right? Right? Let's say your data looks like this, okay? Technically, you don't know what the function is doing in between. You do not know what it's doing, right? Of course, the best possible thing to do is do a straight line, like this, right? However, it's possible that the actual function is doing something like this, right? Okay, and you sampled only on a finite period, okay? So this is the limitation of the table representation of a function. You do not know what happens in between, okay? Even only these points, all you know is that, oh, okay, maybe I should just fit a straight line, okay? However, the reality, just one more sample point, let's say that it was sampled like this, right? Let's say that that point was given as well. It kind of breaks the whole thing, okay? So somehow, I don't know if this is coming through, right? Is it clear what I'm trying to say here, right? Yeah, it's not like always the same thing, okay? It's more like an educated guess, and you have to become comfortable with the type of models that are available to us, okay? Right? Okay, anyways, so that's all I want to say. Well, I guess we'll talk about this more next class as well, okay? On Thursday. Okay, but with that in mind, okay? With that in mind, with that in mind, okay, right? So we now have a new family, okay? The family of polynomials, okay? How many families do we have so far? Exponential. What else?
Periodic.
Exponentials are related to logs, but okay.
Polynomial.
Powers, yes, powers. Related to polynomials too, by the way. Power functions are x to the p for p real numbers. This is x to the p for p integers, right? Yeah, or natural numbers, okay? Okay, what else? Okay, exponential we said. Sines and cosines, somebody said.
Trigonometry.
Trigonometric, what else? We're
Periodic.
missing one.
Does it count?
Rational.
No? Okay. Anyways, okay. So maybe it will come to us, okay? All right, anyways, so we have a wide enough, choice to model. I mean, somehow this is way too much already, but anyways, let's keep adding more, okay? Anyways, so rational functions is, what's a rational function? okay? It's a function that's a ratio of two polynomials, okay? So for example, is sine x over x a rational function? Who says yes? Yes, who says no? It ain't. It's not, right? Because sine of x is not a polynomial, okay? I know it's a bit, you know, we have to use this definition, okay? A rational function is always a ratio of two polynomials in this course, okay? All right, and so the idea here is called an asymptote, okay? What it is behavior at infinity, okay? And so the idea is as follows, okay? So let's say p of x is equal to 1, and q of x is equal to x, right? So then our rational function, r of x, looks like 1 over x, does it not? Okay? And indeed it's a rational function. Is this a polynomial? What's its degree? Degree 0 polynomial, okay? How many parameters? 1. Okay, this is also a polynomial. Degree 1. 2 parameters. One of them is 0, the other one is 1. Whatever, right? Yeah. Rational function, okay? Ratio of two polynomials, okay? All right, very good. And as you know from high school or whatever, right? This is what the graph looks like, okay? This is what the graph looks like, okay? And so asymptotes are behaviors at infinity, okay? And what is infinity? Well, what do I say more than this? Can I draw infinity? So what's happening here is no matter how close you're getting to the origin, so it's like, okay, so if this is 1, this is 0.5, okay, this is 0.25, right, yeah? If you keep getting closer and closer to 0, you're gonna be dividing by 0 at some point, and that number is very large, okay? Similarly, if you approach from the other side, you're gonna be dividing by something that's 1 over 0, but it's approaching from the negative side, okay? So you're going to be dividing by smaller, or it will be 1 over minus 0.5, then it's going to be 1 over minus 0.25, so on and so forth. Negative numbers, they will tend to minus infinity, okay? That's all we're going to say about this, okay? So asymptotes are behaviors where you're essentially dividing by 0, okay? That's the asymptotes in the vertical component, okay? Horizontal asymptotes happen in the horizontal direction, basically, right? Yeah. So what happens with this function as x gets larger and larger, okay, right? Yeah. 1 over 100 is what? 0.01. That's a small number, right? Yeah. 1 over 1,000 is 0.00, so on and so forth, right? Yeah. It's getting closer and closer to 0, okay? Closer and closer to 0. Okay. So eventually, if we wait long enough, we will hopefully reach 0, okay? But tell me in a million years, let's say we're indexed to x as seconds, right? Yeah. In a million years, it's still a finite number, okay, right? It's not 0. It's 1 over whatever, right? Yeah. Or in a million seconds, 1 over a million. That's still 0.00 something 1, okay? So you have to keep going, okay? And keep going and keep going, keep going. So that's all we want to say here, okay? So once again, so asymptotes is behavior at infinity, okay? Now, okay, note the trick, okay? Here's the trick. Does this apply only to rational functions? No. Functions that are not rational functions can also have asymptotes, right? Remember, we were talking about tan, right? Tan was a ratio of sine over cos. Cos hits 0 sometimes, so we have that type of behavior happening, right? So asymptotes are not only reserved for rational functions, they're reserved for all functions, okay? Similarly, you can have vertical and horizontal asymptotes, right? Yeah. But the idea of asymptotes is best exemplified by polynomials, okay? So that's why we focus on this thing, okay? All right. Any questions about this? It's just an introduction in some sense, right? Yeah. So let's see. Asymptotes graphically, we did this, okay? Oh, that's it. That's all we have to say about this, okay?
Yep.
All right, good. Okay, did it crash? Ah, no, it's back. Very good. And now we open this. Let's go to lecture 7 pdf.pdf, okay? Very good.
笑死我了。我目前是
加完下一个
Okay, all right. How did I do this? Like this, right?
其
Control L.
实
我跟你讲
All right, okay, so this is lecture 7, okay, whatever that means. Okay, so we're gonna shift gears, literally, okay? So we're literally shifting gears, okay? What's happening? What is this? 2.1, 1.7, 1.8, right? Yeah, who wrote this? Whose idea was this? I don't know. Maybe it was my idea, okay? It wasn't, okay? But it's best exemplified. You have to understand, once we go through the context, it all makes sense, okay, right? Yeah. You know what the idea is, right? This is about velocities and this is about general limits, okay? And somehow if you have a physical grounding, if you have a physical phenomenon, you can kind of, understand this abstract concept a bit better, okay? All right, anyways, so section 2.1, distance, velocity, speed graphs, matching motion described in words, and describe motion matching given graphs, okay? Define instantaneous velocity, distance versus time, blah, 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 okay, right, yeah? So we're going speed is equal to distance over time. Do you remember this or no? Who remembers this? No? Okay, so I'm gonna tell you a story, okay? So, okay. So where I'm from, okay, we have to, like, when we're learning to drive, this actually happened. The friend is my brother in this case, okay? So we had to, like, it's actually funny. We had to learn how to drive, but our sister was taking the test and we were like 12 and 13 at the time. She was like 20, 21, I guess, right? And we have to learn how to do manual, right? Yeah, there's automatic. Who knows what's manual? Right? You have an idea, right? Sort of, right? Okay. Who doesn't know what's manual vitesse? What is it called? The speeds, right?
I don't know.
Okay, some people even know how to drive it, right? Yeah. Yeah. So whatever the story is, we have to learn how to drive manual gear, right? Yeah. That's the gearbox was manual, right? Yeah. And so we had to practice, and our sister could never. She had big trouble passing the test. But we would practice, these little kids, 12, 13, right? Yeah, driving around our neighborhood. So you're driving your car in your neighborhood, and you have found a straight road close to your home. Okay. You want to practice your driving skills, especially driving in reverse. Your friend, which is my brother, okay, right? I guess, okay, whatever, who knows the distances between each house, steps out of the car. He estimates the following distance relative to where he's standing. Okay, so what's happening, right? Yeah? Okay, let's drive around back and forth, right? He gets out here, okay, and I'm gonna start driving like this, okay, right? Yeah. So at time 0, he has a timer. We're at the same location, okay? Then I start driving, okay? 10 seconds in, I'm 150 meters away. 20 seconds in, I'm 250. 30 seconds away, I'm 300 meters, okay? 200, okay? So what happened, okay? 100, 0, and this is the distance to my friend is 100. So what happened here? What could have happened, right? Yeah. Clearly something funny happened here, right? 250, 300, 200, right? And then something funny happened here. What could have happened? Yes? Yeah, exactly. So I was driving that way, but then I went back, right? Yeah. And then I'm over there, 100 meters away from him over this, okay? In a circle, but let's say straight lines, just to idealize, okay? So here I stopped somewhere here, and then I started reversing, and I went past him, okay, right? So, whatever, okay? Quite fast, oh yeah, in reverse. Okay, so that's the story, okay? That actually happened, okay? What your friend has tabulated is your position relative to him, okay? Your friend, he is the frame of reference with respect to which the scale on the orientation of the table is determined, okay? So the distances are from me to my friend, okay? All right, so these are the distances, same table as we had previously, okay? But my position relative to him, that has an orientation, okay? Positive when I'm going in a positive direction, negative if I'm behind him, okay, right? So I'm 150 meters away from him, 250, everything is fine here. The only difference is now I am behind him, okay? And this indexes exactly that, okay? The position or the displacement, you know, if those of you who remember high school physics, right? The displacement is, it's a vector quantity is the word, yeah, okay? Whatever that is. Anyway, okay? All right, good. So the displacement is nothing but the change in the position of an object from the initial position to the final position, okay? So x final minus x initial is the relative displacement, okay? Right? Okay, so we can now continue to tabulate our table, or continue our table. Note that the displacement is between 2 points, okay? So let's try to fill up this table, okay? You all have the PDF, okay? Let's spend like 2 minutes trying to fill up this table. Okay, so del x is xi minus xi minus 1. So for example, x1 minus x0, right? Then it's x2 minus x1, x3 minus x2, and this is what, well, or x150 minus x2, yeah, whatever, right? Either one works, okay? So, can it be, why not? Displacement, yeah.
嗯，是那个 delta x。
哦，它这个意思。这填一下呗。
不是，那它第一段它这个距离它是算降速的。
So yeah, so for example, 250 minus 150, right? Yeah. X final is 250, X initial is 150. Okay, then 300 minus 250, so on and so forth. Okay. Right? So try to fill it up. Let's see if we all get the same answer.
什么？
它减一就是说，比如像第五排减再减一就是第4排，
哦，
对吧？它下面那个，对对对。
我懒得写那么多数字。它就按你算哪一段走多少。
是。
这么高级？
嗯？我还等着回去弄支笔。还要回去把我
这个
那个
需要。他的备忘录太他妈傻逼了，这个他的备忘录功能太他妈傻逼了，我他妈经常时不时就触发一下。
是 derivative 吗？
什么 derivative？我们讲 derivative 的吗？
是 derivative 的。
看一下你。
这多简单。
x 那个 f 不是，好像
M
不是。
位置吗？
这还没学到这儿吧？
不是 M 位置。
好像它不是。
Okay, good, bad? Yes, no, maybe? All right, so it's between 2 points. So if this one had 1, 2, 3, 4, 5, 6, 7, 8, it had 8 entries. This table is going to have 7 entries, right? That's the point, okay? All right, so what do I put? So it's kind of like, you know, you draw like a line. So it's not all in a straight line, yeah? Unless, well, whatever, okay, right? Okay, so what's this one? Del x is for, so what's x150 minus x0? 150, next one, 100, 50,
Minus. Negative.
negative, exactly, negative 100, negative 100, negative 100, negative 100, right? Yeah?
Yes.
Okay, so this thing takes into account the direction, right? Yeah, positive, okay, right? Yeah. So we're making this a bit more refined, whatever that means. Okay. So the key point here is that the displacement is different from distance. Okay. That's the key point here. All right. Very good. Okay. Okay. And now let's say that me and my brother were kind of whatever, right? Yeah, we're bored and we don't have a speedometer. So we want to know how fast we're going, right? Yeah, or I was going, okay? So this is expressed at the rate at which your position changes over time. Remember, they say speed is distance over time, well, velocity is, displacement over time, right? Yeah. Now, since the table is nothing but a snapshot, okay? So look what's happening here, right? Yeah. This table, my brother, like one way to think about this is he's taking a photo every 10 seconds, okay? A photo is different from a video, right? A video is like kind of continuous, even though it's still 30 frames per second, whatever, right? Yeah. The video contains a more refined, number of steps, okay, right? This only contains what, 8 snapshots, okay? So we have to do with these 8 snapshots, okay? And because we don't know what happened in between, just as we drew in that graph previously, right? We don't know what happened in between. The best thing we can do is do an average that happened between each snapshot, okay? All right, the table only has snapshots of what was happening, so we will be averaging. We define the average velocity as what has happened between 2 separate snapshots or time frames, okay? More specifically, if x1 and x2 are your positions at time t1 and t2, the average velocity is, this is nothing but rise over run, right? Yeah? Or speed is equal to distance over time, okay? So that's our starting point, okay? So v bar means average, is nothing but del x divided by del t, okay? Which is x2 at t2 minus x1 at t1, t2 over t1, okay? All right, very good. So now we can fill up our table, okay? Sorry for, yeah, okay. So let's try to fill up these v bars. So we have the del x's, right? All we need now are the v bars, okay? And so v bar is nothing but del x over del t, which is nothing but x over the xt1, well, x at t I minus x at ti minus 1 divided by ti minus ti minus 1, right? Okay? So let's try to fill up this table. We have this. Let's try to get the v bars. Okay, so once again, since del x is it's somehow between 2 points, the average velocity is between 2 things, okay? 2 snapshots. So we had 8, that's going to collapse to 7, okay? 8 entries. Velocity can be negative, speed cannot be, yes. Okay. Okay, so let's do that and then we'll take a break, okay? How about that? It's been a long day, no? 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 Whose day is just starting? No? Okay, good.
这老师我真的服了，这老师我真服了。
我是不是可以直接扩展起来呀？就是下一排，这里写的吗？微屏。啊。好像是10，还真是。
Okay, so we have the answer ready? I think we do, right?
Yeah.
Right? So the answer is
15, 10, 5.
divide everything by 10 and yes, exactly. So look, the time steps, they're always the same, right? So ti minus 1 is always equal to 10, okay? That's the point. So everything you take in this del x table, right? D bar is nothing del x but divided by dt, so you just divide by 10, okay? So it will be something like meters per second, right? I think. So what's the first one? 50 meters per second? What is that in kilometers per hour? Is it slow or fast? Please tell me it's fast, okay? What's if 15 meters per second? How many is that in kilometers per hour? How fast? Tell me I was going fast, okay? Yeah. Don't tell me I was going slow.
It's pretty slow.
It's like about 50 in the first 10 seconds.
50. I went 0. That's great. Yeah. Okay. This table is fake, by the way. Okay. Right. The story's true, but the table's fake.
Okay.
But I'm glad that it's not slow. Okay. Right. Okay. Is it clear the game that we played here? Right. So the point is this: given displacement, if you assume speed is distance over time, right, you can get the velocities. Okay. Or you can get the velocities displacement over time, right? Yeah, what's speed? Speed is distance over time. Distance is this, okay? Right? So if you want to look at the average speeds, right? The only thing that changes is this one becomes, what is it? Everything is positive, okay? That's it, okay? And indeed, speed is nothing but the absolute value of the velocity, okay? Right? If we remember from high school. All right, anyways, let's take a 10-minute break, okay? And then we'll go on. Oh, and then we'll do this stuff. Very nice.